In this section, we're going to discuss homogeneous linear systems. So let's go ahead and start off with the definition. What is a homogeneous linear system? So a linear system of equations is called homogeneous if it can be written as a matrix equation ax equals 0. Okay, so notice first, any linear system of equations can be written as a matrix equation, right? Generally, a linear system of equations, we saw, can be expressed in the form ax equals b for some vector b, right? Where a is the coefficient matrix. A homogeneous linear system of equations, then, we write the same thing down, except it's the special case where vector b is the zero vector. That's what makes it a homogeneous linear system of equations. All right, so let's look at a brief example. So if we have 2x plus 4y equals 0 as our first equation, and maybe x minus 3y equals 0 as our second equation, we just have two equations. This is a homogeneous linear system. And the key that makes it that is the zeros on this side of the equation. Okay? If we rewrite this as a matrix equation, our coefficient matrix is 2, 4, 1, negative 3. Our variables are x and y. And on the other side of the equal sign, we have 0, 0. Okay? So this is A, this is vector x, and this is vector 0. Okay? So we do have ax equals 0. The 0 vectors on the other side, which means the 0 vectors on the other side of the equal sign here. Just zeros on the other side of the equal sign here. That's what makes it homogeneous, is those zeros. Okay? If I considered another system, very similar, 2x plus 4y equals 7, x minus 3y equals 0. This system is not homogeneous. Okay, if we write this as a matrix equation, we have the same coefficient matrix. Same variables x and y. But on the other side of the equation, our vector b is not just the 0 vector, it's the vector 7, 0. So we have a x equals some non-zero vector b. And so that's why the equation is not homogeneous. We have something that's not 0 on this side of the equal sign. Okay? Now, notice that when we have a homogeneous system of equations like this one, we are guaranteed to always have a solution, at least one. The system is guaranteed to be consistent because I can choose all the variables to be 0. A homogeneous linear system is always consistent because setting all variables equals to 0 is a solution. And we could see that here, right? If I set x equals 0 and y equals 0, 2 times 0 plus 4 times 0 is 0. 0 minus 3 times 0 is 0. It solves the system. And for any homogeneous linear system, it will solve the system. Generally, for a non-homogeneous system, like this one, we may have a solution, we may not. Certainly 0, 0 is not a solution. I can't just set all the variables equal to 0 and solve the system. It will solve the second equation, right? 0 minus 3 times 0 equals 0. Okay, but it doesn't solve the first equation. 2 times 0 plus 4 times 0 is not 7. Okay? But a homogeneous linear system is always consistent. Always has at least that one solution. It might have more, but it always has at least that one solution where you could set all the variables equal to 0. All right? Let's think about solving a system. Let's consider this system in particular. Okay, how would we actually go about solving this system? Okay, well, we know to solve a linear system of equations, we can use an augmented matrix. The left side of the augmented matrix is the coefficient matrix. The right side are the zeros. Okay, and then we could get this thing into reduced row echelon form. This one's simple enough. I'm going to go ahead and do it by hand. Okay, so first I'm going to swap row 1 and row 2. So if I do that, row 2 becomes row 1. What was my row 1 becomes my row 2. Okay, this is going to be my pivot. I'm going to get zeros below that pivot. So let's do R2 minus 2R1 is my new R2. So I'm leaving row 1 the same. And row 2, I get 0, and then what? 6 plus 4 is 10. And then 0 plus 0 is 0. Okay. Let's get a 1 here. I'm now in row echelon form, by the way, right? I've got that stair step pattern. In row echelon form, I want to continue and get it into reduced row echelon form. So that means all my leading terms should be 1. Every column that has a leading term, all the other entries should be 0. Okay, so I've already got this leading term to be a 1. Let's turn this leading term to 1. So let's take row 2 and multiply by 1/10. That's going to be my new row 2. I get 1, negative 3, 0, 0, 1, 0. And finally, we're almost done here. Let's do, we need a 0 here because we have a leading term here. So all the other entries in a column with a leading term have to be 0. So let's get a 0 right here. So that's going to be row 1 plus 3 row 2 is my new row 1. So that gives me 1, 0, 0, 0, 1, 0. Okay, so we see we do have a solution, right? My first variable is equal to 0, my second variable is equal to 0. We have that solution. We call this solution, by the way, for a homogeneous equation, the trivial solution. Okay? Setting all those variables equal to 0, this is called the trivial solution. It's trivial because it's always true. We don't even have to think about it. For a homogeneous linear system of equation, we always have this trivial solution. Okay? We may have other non-trivial solutions, but we are guaranteed for a homogeneous linear system to always have that trivial solution. We see that here. In this case, we have only the trivial solution where all my variables equal 0. Okay? But I did this for another reason. I solved this system because I want you to pay attention to what's happening to the augmented part. With this homogeneous system, that augmented part is all zeros. So if I swap two rows, it stays 0. If I add a multiple of one row to another row, it stays 0. If I multiply a row by a non-zero constant, that augmented part stays 0. It always stays 0. No matter what elementary row operation I do, it always stays 0. So am I really gaining any information by adding this 0, 0 over here when I know by the time I get down here, it's still going to be 0, 0, no matter what elementary row operations I do? Not really, right? It's not really doing much. Doesn't have much of a purpose. When we're solving a homogeneous linear system of equations, we often leave off the augmented zeros. We know they're zeros. And so writing zeros at each step, it's just extra writing because we know every elementary row operation, those zeros in the augmented part would stay 0. Okay? And so if we leave them off, we could do all the elementary row operations, still get the coefficient matrix, just focus on that coefficient matrix, and then we just mentally know, oh, this is a homogeneous linear system. The augmented part, which I'm not bothering writing, is all zeros, and you could solve it from there. So this is customary. There's nothing wrong with writing the zeros here. Okay, there's nothing wrong with writing these. Technically, it's correct, but it's extra writing that you don't need to do. So customarily, when we are solving a homogeneous linear system, and the augmented part of the system of equations is all zeros, we usually leave that augmented part off. Just focus on the coefficient matrix, because no matter what elementary row operations we do, once we do all the elementary row operations we want, that augmented part will still have just zeros in it.